Hello, Chemistry 150 students. It's Friday and we have another problem solving sessions. In today's problem solving session, we are doing the gas laws and we're working on a chapter 6 problem, number 122, which deals with partial pressures and mole fractions. So the problem reads, a mixture of 8 grams of methane, and you should know that this is methane because it is one carbon, and we've done our organic nomenclature. So a mixture of 8 grams of methane and 8 grams of xenon is placed in a container, and the total pressure is found to be 0.44 atmospheres. Determine the partial pressure of methane. So we see that this is a mixture and they give us grams. We could easily convert grams to moles using molar mass. And the reason why that's important is we know that the total pressure of this mixture is 0.44 atmospheres. And we also know, according to Dalton's law of partial pressure, the total pressure is a sum of the individual pressures. And that's why we're trying to figure out the partial pressure of methane. Now, if we had, um, you know, temperature and volume, we could use the ideal gas law constant and the ideal gas law to solve for pressure of methane using 8 grams and converting that to moles and doing it that way. We don't have that. We simply have the total pressure and we have the grams of each component. So we have to go about it a different way. So that's where we start using the term mole fraction. It's a ratio. So the ratio of the partial pressure of a single gas is basically total pressure is equal to the mole fraction. So what does that mean? Well, like I said, we could rearrange the ideal gas law equation of PV equals nRT and solve for pressure. So we see nRT divided by V. The subscript A means the component, the partial pressure that I'm looking for, over the total. So this is a ratio, part over whole. Well, when we cancel out the RT over V, basically the ratio of partial pressure over total pressure is equal to the ratio of partial moles over total moles. And that is the mole fraction. So by dividing part over whole, we get a mole fraction. And in the book, it shows it as the x. The mole fraction is the whatever component you're looking for, the amount of moles part over the total moles. Now, if I substitute this x for this ratio right here, and I want to solve for partial pressure, all I would have to do is multiply both sides by the total pressure. And that gives you this equation. So once I have the mole fraction, I can easily multiply the total pressure by that mole fraction to get the partial pressure. So let's go ahead and do that. So first I got to get the moles. That way I can get the mole fractions. That's pretty straightforward. The moles of methane, they tell me I have 8 grams. I can look up the molar mass in the periodic table, and I have in bold 2 sig figs, but I won't round to the end. But I know it's 2 sig figs because the 8.0 is 2 sig figs. Then I figure out the moles of xenon. And again, 2 sig figs, so you see the two significant figures, the first two, that count. Again, these are leading zeros, they do not count. These are the 2 sig figs that are significant. I'm going to wait to round. I also notice even though I have 8 grams of each, because the xenon is a much larger molar mass, I have fewer moles. Now, when we talk about pressure, pressure is directly proportional to moles, and we see that here solving for the ideal gas law. So it doesn't matter the mass, it only matters the moles. So because we have more moles of methane, if you think pressure is force per unit area, and like in my video discussing pressure, really the force, you can think of it as collisions on the side of a container. Well, if there's more moles, there's more collisions on the side of the container. And if there's more collisions, there's more force per unit area and a greater pressure. So it makes sense when I do the mole fraction for methane, part moles of methane over whole moles of methane and xenon, I get a much larger mole fraction of methane. So when I multiply the mole fraction by the total pressure, as this equation tells me, I can get the partial pressure of methane, and I see clearly that it's 0.39 atmosphere. And again, two sig figs, two significant figures, and it makes sense that the methane has a much larger partial pressure because I have more moles of it. So I hope you enjoyed this week's problem-solving sessions. And as always, if you have any questions, please let me know. Thanks.